still yet to be replicated. Are 5s and 3s okay? 5 to 3, 5 to 3, 5 to 3, 5 to 3. Everybody's happy. I guess there's a 5' in there. Now, here's the question. This shows accurate replication. The next base is going to get added here. And the next base on that strand is going to get added here. There's a really important detail. Perhaps people noticed this. On one of your strands, if you followed the rules, you could just keep writing letters. Was that true on both strands? Can somebody tell me what you had to do on the other strand? Yes. If I'm guessing right, this was the original part he replicated over here, and this would be the original part that replicated over here. This strand is going to grow here. Once you've replicated to here, you can't go any further. This strand, when it replicated to here to its 3' end, it just goes on merrily along, keeping on replicating. What has to happen on this strand? What had to happen to replicate these bases here? You had to start over. That's exactly right. So that on one strand, the 3' end was here, and it just keeps going. And on the other strand, you actually have to go back and start over. I'm going to draw a cartoon of that in a second. But did people see that? That if you just wrote your letters, you probably didn't see it. If you very carefully followed the rules about 5s and 3s, you would notice that the two strands were different. Okay? So let me draw a cartoon of that and show you what I mean. So Paul, thank you very much. And let's go back to the computer. So here. Let me give myself a little more space. So we unzip some more. This would be 3 and 5 and 5 and 3 of the original. And our old DNA that we made was here. And this one had its 5' and its 5 and 3, 3. So this was the situation when when Paul unzipped his and all of you guys unzipped theirs, it looked like this. Okay? And if you go to replicate, and we'll put that, say, in another color. Let's do that in green. Can I add bases right here? Let me draw it. Let me put it this way. Can I add bases right there? Yes, it's a 3' end. So this strand replicates, no problem, keeps on going. All right? Blah, 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 blah. New 3' end. Right? Can I add to there? No, the law says no way. So I can't. So what do I got to do? Start over. What does it mean? Do I start here to replicate? Where do I start? In the fork, right in the middle of the fork there. I have to like the thing that makes the DNA has to jump back and start over. So that's what you do. You actually restart, and you make DNA. Oops, yeah, a new piece of DNA like that. 5' to 3', blah 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 blah, like that, right? Did questions about that? Because that's actually a really big deal, it turns out. That the two strands are different because of those rules. Yeah. How do you start over? There's an enzyme, like you saw in the video, that makes the DNA. In this case, it rolls along. In that case, it actually has to come off the DNA and start over. So the enzyme that does it detaches from the DNA and reattaches. So it's all right. Actually, let me make a note about that, and then let me do some for questions. Leave it. I'll get you 1 sec. The synthesis must restart. It is what's called discontinuous. Because this, where here is DNA synthesis continues, or I guess is DNA synthesis is continuous. It does not stop. Because of the way the 5' and 3' ends work. Let me label these, and then I want to take questions. This is called the lagging strand, and this is called the leading. Because when they very first found this, they're like, oh, the enzyme that makes DNA can just totally roll along that bottom strand continuously. So it's going to go fast. It's going to go faster because it doesn't have to start over. The other one up above is going to be lagging behind because it's always going to have to do a bit, come back, do a bit, jump ahead, do a bit, jump ahead, right? Turns out that the whole process is very coordinated, so they happen about the same time. Basically, the leading strand synthesis is held up waiting for the lagging strand, so they go together. But in any case, the two strands are different. The most important thing is that the reason why it does this is because of the rules we just talked about. Levi, where are you? Yes, question. So what are the different colors? So black is the starting DNA. Blue is the first bunch of DNA I made. It corresponds to the colors up above. So the first bunch we copied, I copied in blue. The second bunch I copied in green. Why does it have to start there? Because of the rule you can only add to a 3' end. That's what the law says. So you have, in order to be able to grow that way, you have to restart. So it unzips, copies that, and then it unzips more and starts at a new spot. Okay. All right. Yeah. Yes. There's a couple important things. Lagging strand synthesis. There are gaps in the backbone which actually get fixed by an enzyme called DNA ligase. Another important thing, is the lagging strand always going to be the top strand? No, it depends on where the 5s and 3s are. Okay? All right. There's one more thing I want to say, and that's about just a little bit about mutations. Okay? That is, they are, they're mistakes in DNA replication. DNA is replicated by an enzyme called DNA polymerase, or DNA Pol for short. It has proofreading. And that leads to one error in about 10 to the 10th bases added. All right? So DNA polymerase is the name of the enzyme that replicates DNA. It has proofreading. It does its best to put the right base in, and it even checks it. It still makes errors, about one error in every 10 to the 10th bases. What's that? How does that correspond to real life? Let me get these numbers right. If you were typing, like on your keyboard, 60 words a minute, which is pretty fast typing, and you typed 24/7, 365, an error rate of 1 in 10 to the minus 10th would mean making a typo every 64 years. So you'd be typing for 64 years and make only one mistake typing that fast. That's how incredibly accurate it is. And the reason is you don't want to mess up your genes. But sometimes DNA polymerase makes mistakes. The other way you get mutations are mutagens. That is, chemicals or radiation cause mutations if the damage to DNA is not repaired in time. We'll talk more about this later. And also, both are always random. The other thing is kind of a little tiny bit of mutation trivia. There's about 3 billion base pairs in each of your cells. If everything worked perfectly, your DNA would be exactly the same as what you got from your mom plus what you got from your dad. It turns out, on average, there are 36 mutations differing between you and what you got from your mom and dad. So in that somewhere, 36 different nucleotides changed. And we'll talk about what the consequences of those are later on. Let me do the clicker question, and we will call it a day.